Let's make an example for the Sturm-Liouville problem. So example, this is a second order BVP, which is minus y double prime equals to lambda y, with our boundary conditions is y0 at x equals to 0 and yl. So final point x equals to L, that is also equals to 0. And let's first check whether this is a Sturm-Liouville problem or not, okay? So first, let's see the format. What is the SL problem format for the ODE? It's minus d over dx, px y prime plus qx y equals to lambda omega x y, right? So this is the format for SL. And to be noted that px needs to be over 0, qx needs to be over or equals to 0, omega x, which is the weighting function, is also need to be over 0. Let's check what is our px, qx, omega x for this problem site, okay? So this is minus y double prime on the left-hand side. That means our px need to equals to 1. So that you have minus y double prime. Then what is our qx? Qx, there is no y term here, so it's 0. What is our omega x? The omega x is 1 for this one. It's very simple. So we have our coefficient px, qx, and omega x all satisfy for the conditions of SL problem. Then at least for the format, they are SL problem. Then let's see the boundary conditions. So we have y naught equals to 0, yl equals to 0. What is our homogeneous boundary conditions need to be? The homogeneous boundary conditions for the SL problem needs to be satisfied alpha 1 y, for here will be y naught plus alpha 2 y naught prime equals to 0, beta 1 y, the final point will be L, plus beta 2 y L prime equals to 0. So here, for these boundary conditions, we have alpha 1, right, equals to 1, alpha 2 equals to 0, beta 1 equals to 1, beta 2 equals to 0. So at least one of them is non-zero. At least one of those beta are non-zero, so they satisfy for the homogeneous boundary conditions for SL. So this is indeed a Sturm-Liouville problem, so SL problem. Okay. And let's solve the what need to be finished first. We need to get what is the eigenvalues, then we need to correspondingly get our eigenvectors, right? So our eigenvalues, the eigenvalues, that is the step 1. This is a second order ODE with a constant coefficient, so that the solution format will be an exponential solution format. Then we have the solution format should be look like an exponential function. So e to the rx. That is our gas solution format, e to the rx. Then we can solve this problem set, which is r squared minus r squared e to the rx will be equals to lambda e to the rx. Then you have basically your r will be equals to plus minus, right? R squared will be equals to minus lambda. And let's make an assumption for the lambda, because whether this lambda is positive, negative, or zero, that will lead to different roots of R. So first, let's make an assumption. My lambda is positive. So UR will be equals to plus minus lambda I, right? This is a complex number, plus minus roots of lambda I. Then when you have this solved, what is your solution format look like? It will be exponential of plus minus lambda I x, right? This will be your solution look like. And when you have the solution look like an exponential part with complex term I there, you can write as a sine cosine format. So e to the plus minus I theta will be equals to cosine theta plus minus I sine theta. Okay, so for our case, this e to the plus minus root of lambda I x will be equals to cosine root of lambda x plus minus I times sine root of lambda x. So we can transform our exponential into a sine cosine form, and let's for you transfer to sine and cosine form, it will be easier for us later to plot what is the physical 2D plot for this solution site. So we will use the sine cosine format. And if we write our final solution of this homogeneous ODE, right? It will look like y. It will be a combination of linear independent solution, which is cosine part and sine part. So it will be C1 cosine lambda root square x plus C2 sine root of lambda x. Okay, then you basically can use your boundary conditions to help you to find out what is your C1, what is your C2. Okay.